All right, so we're moving on from flexural deformations, and pretty much anything to do with bending. You'll see, um, sort of as we've seen before, it's very difficult to separate shear stress completely from bending stresses, but we're going to start to focus on effectively how are we calculating the shear stress in a beam that is subjected to some sort of applied load, right? So in general, from a strength standpoint, in terms of making sure that the capacity of the beam is greater than the demand, there's two things we've got to check. We've got to check that it's got the proper flexural capacity to meet the demands. We've also got to check that it has the proper shear capacity to meet the demands. As I've mentioned, I think many times, and as you'll see here, the sign convention we use for shear stress isn't that important. For shear force, the sign convention that we use for shear stress, however, is actually pretty important, and we will get into that. But there's a good sort of clear definition for that. Okay, so if we're looking at shear stress in a beam, I've drawn a simply supported beam here. I'm showing a depth because I want to sort of zoom in a little bit here. And so if I take a cube here, and this guy, we're going to call it an infinitesimal cube, right? So this guy actually has, dimensions that are very small, and we refer to those as dx, right? And if you notice the downward force that's being applied to the member, and then we've got an upwards reaction over here, right? Obviously we have an upwards reaction over here as well. But if we look at how this force ends up, or a portion of that force ends up being balanced by that reaction, it's actually got to be carried through the material at every level, right? And so what we have necessarily is a shear that develops, and we're going to call this tau xy, right? So shear is, sometimes it's referred to as sigma, like our other stresses, but in many cases, particularly in your textbook, I believe they call it tau. So you think about it as the same as sigma. And if we're going to zoom in to what that cube actually looks like, so let me do that here. Right. Oh, sorry about that. Let me draw that again. There we go. So, so that shear force, or shear stress, sorry, is here, right? And we call that tau xy. Right? But there's a lot of other stresses that are on this cube, right? And so what I'm going to do here is, without really explaining too much about kind of where they come from or how to calculate them, I'm just going to draw the positive sign convention for all of these stresses, and then we'll sort of talk about them a little bit, and then I'll get into how do we calculate the shear stresses. So on each face, we actually have two stress components. We have a normal stress, which could be due to something like flexure, right? And those are going to have repeated roots, right? So sigma xx, or in the case of this upper portion here, this would be sigma yy, right? Because it's on the y face, and I can draw a coordinate system here. So same one we always use, x and y, right? And then I can draw my shear force that's here, right? And those axial stresses have to be balanced by axial stresses on the opposite side of the cubes. And the shear has to be balanced by opposite shears on the shears going in the opposite direction on the other side of the cubes. So let me erase this and put this down here. So this guy we're going to call tau xy. This guy we're going to call tau yx. This guy is also tau yx. This guy is tau xy. This guy is sigma xx, and this guy is sigma yy, right? So that is our positive sign convention. And let me kind of explain it a little bit here. So I'm going to have sigma ij, right, where I is the direction perpendicular to the area. Right? So let me explain that a little bit. If I look at this face here, right, I'm going to call that an X face because the perpendicular direction is in the X direction, right? So the direction of a face is the normal of the face, right? So that is the area, right? And then J is the direction of the force. I'll put stress here, actually, because we're now at the sort of infinitesimal level, so that's the stress, right? But that's basically the direction of the arrow, right? So if you can see a stress that is acting on the X face, right, and it is going in the positive X direction to the right, that would be a positive stress, right? So that is sigma positive X times positive X, right? And actually, let me not do it that way. So basically what I have is two positives. Both the I, which is the direction of the area, is going in the positive X direction, and the arrow itself is going in the positive X direction. That defines a positive sigma XX. Okay, so let's look at this guy over here, right? Is that a positive sigma XX, right? And the answer is yes, because now its face that it's acting on is a negative X face, right? So it's moving in the negative X direction. The normal to that face is moving to the left, right? Which is the negative X direction. But the arrow is also moving to the left, right? So it's all the arrow is moving away from the face. That's always going to be positive. This is, by the way, the exact same sign convention, internal sign convention, that we used for axial members, right? So where we always drew the force moving away from the face, right? Here I'm just giving you a little bit more sort of insight into, where this comes from, right? And this, by the way, is also applied to the shear stresses, right? So if we look at tau xy, what does that mean? Well, it means that it's on a positive X face, right? And it's in the positive X direction, right? And so this tau xy here, right? That is a positive X face, right? And it is moving in the positive Y direction, so it's positive, right? And this one, oh crap, look at what I did. Sorry, guys. Stupid me, put the arrow going in the wrong direction here. So this one here, now I'll change this, or go over it in green. You can see the opposite side of the cube, that is also a positive tau xy. It is on a negative X face and it's moving in the negative Y direction. So negative times negative is a positive. Okay? And similarly, tau yx, that's on the top one here, is on the positive Y face, and that is moving in the positive Y direction. Sorry, positive Y face moving in the positive X direction. And this is on a negative y face moving in the negative x direction, right? So that's why it's a mixed sort of, xy or yx as opposed to xx and yy. So anytime you see a repeated root on a, or repeated index on a stress, it means it's a normal stress, right? Same face, same direction, right? Anytime you see an index that is not repeated, so xy, or if we go into 3 dimensions, zy, yx, etc., those are all shear stresses because they're acting on a face and they're moving in a direction that is not perpendicular to that face, right? Okay, so couple things, right? One, if I sum moments, right, about any point here, right, if tau xy and tau yx do not equal one another, you can see there is going to be a net sort of rotational force here, right? So moment equilibrium gives us, so I will write this, if I do sum of the moments, it doesn't matter about what point, you will get that tau xy equals tau yx, right? So this is really important. What this is saying is that the horizontal shear force, or shear stress, and the vertical shear stress at any point have to be the same. And you'll see in your book, they pretty much don't talk about tau yx. Everything is tau xy, right? So in 2 dimensions like this, we really only have 3 components of stress. We have sigma xx, right, which could be like a bending stress that you guys had calculated. We have sigma yy, right? And we have this tau xy, which is the shear stress, right? Nothing else. Okay, so that is a really important thing because, in fact, what we're going to do is when it comes time to calculating the vertical shear stress in a member, we're going to actually calculate the horizontal shear stress because it's easier, and then we're going to invoke this to say, well, the horizontal shear stress and the vertical shear stress are the same, right? So that's how we're going to get our vertical shear stress, right? And then the other thing that I want to point out, and I'll sort of do this in black here, and I'll try to make this a dashed line, right? So I am going to call this guy the area, right? So what that is, and if I maybe draw this, where do I want to draw it? Let me draw it over here. Let me do it here. So if I draw this beam kind of in 3 dimensions here, like that, this area, let me do this again with black, that area there, right? That is the area that shear stress tau xy is actually working on, right? So just like if I take a normal stress, I take a force and I divide it by the area that it acts on to get a stress, right? Here we're going to do the same thing. We can take the shear force that you guys had calculated in your shear diagrams, and somehow that shear force is distributed over this area as a stress, right? Well, we'll talk about how we actually calculate the way it's distributed. But the important point at this stage is that shear force that you had calculated actually is the integral of tau xy over that area, all right? So this is another thing we need to box because we're going to use this, right? So that is integrated over that area. And basically what this amounts to is that the sum of forces in the y direction have to equal 0. So I've got a shear force that's being applied to a cross section, and that shear force is being balanced by the shear stress that is in the, from that cross section that's counteracting that shear force, right? Okay, so let me move to shear stress and beam. So up until this point, really what we've been doing is just me defining a little bit about how we sort of the nomenclature surrounding stress terms, right? So the first term again is the is related to the perpendicular area that the force is acting on, and then the second term is related to the direction of the force, right? So in general, stress is what they call a tensor. It doesn't have a single direction like a vector. It actually has two directions, right? One is the area it's acting on, defined by the normal, and the second is the direction of the force. Okay, so now let's zoom in to, let me actually redraw that beam. I'm just going to draw it a little bit smaller here to give me a little bit more room. And then we're going to zoom in and we're going to take a look at what is actually happening kind of internally here. Okay, so that's my force. And now I'm going to draw two segments here. So this is C and this is D, and they are separated by a dx. And don't let the dx, confuse you. I know it confuses a lot of students. It's just a really small dimension, right? So C and D are right next to one another. If there's a change between them, I could just take the difference and divide it by that dx, right? And that gives me the change, right? The rate of change there. Okay, so if I take this guy, take this guy out and redraw it here, right? What I'm going to have is I'm going to get a shear force down, then the shear force up on the other side. Notice that that is our positive sign convention for shear force. And then I'm going to have my internal moments, right? So I will call this guy the moment at cross-section C, right? So this is cross-section C, this cross-section D. This is the moment at cross-section D. This guy here is dx, right? And then I have a shear, right? And notice that the shears are the same, right? You could see that actually from the beam that I've drawn there. The shear in that region is constant, right? So now if I sum moments about D, that has to equal 0, right? Again, we'll do right-hand rule as positive. I'm going to get a minus C, because that's coming in as a clockwise moment. I'm going to get a plus MD, and then I'm going to get a minus, V times dx, right? So dx is the moment arm, right? So V is going upwards on the left-hand face, the C face, and its moment arm is dx, right? So I'm summing moments. If you wanted to do this in blue, let's say I'm summing moments somehow, let's say about that point, right? So that dx is the moment arm for V. All right, so when I do that, you get that V equals md minus mc divided by dx. Divided by dx like that, or it equals the change in moment, dm, divided by dx, right? So what is that saying? It's saying that the shear is the slope of the moment diagram. That's exactly what it's saying. Now, we already know that because I showed it to you when we were calculating shear and moment diagrams in the previous topics. But this is now us deriving this just by looking at the equilibrium of a small segment of the beam that we've kind of pulled out here, right? All right, so let me move to the next thing that we need to do. I'm now going to use green, but I'm going to redraw. Let me just make sure. Yeah, something like that. So I'm going to redraw this guy. So this is C and this is D, right? And now instead of just drawing the moments, I'm going to go a step further and I'm going to draw the stress distribution. Right? So on the left-hand side, my stress distribution looks something like this. Like that. So I'm going to call this sigma D, right? So that's just my, it's actually sigma XX, but it's, you know, on the D face, right? And so this guy here is M sub D times Y over I. You guys already know that, right? Okay, so then I can come over here and I can draw my stress distribution on the C face. So this guy we're going to call sigma C. Again, it's sigma XX, but it's on the C face. And this guy here is M sub C times Y over I. Right? And that dashed line you see there, that is the neutral axis. And you can see both of the stress distributions cross zero there. And that's sort of the definition of the neutral axis. And this guy here is dx. Right? So hopefully everybody understands this. Right? So it's just this same diagram that we have here, but I'm pulling off those moments and I'm showing their stress distribution. Right? So that's all that's happened here. Now, if I move over to the right here, right, I'm going to try to keep the neutral axis in exactly the same place, like that. Then I'm going to make a cut, and I'm going to retain just the top part here, right, of that member, of that, sort of free body that I pulled out. So that is dx. Right? And now what we have is my stress distribution. Do it again. All right, so my stress distribution looks something like this. Right. And then over here it looks something like this. Like that. And again, this side, so this is sigma C, this is sigma D, so this is MDY over I, and this guy here is still MCY over I, like that, all right? And now this distance above the neutral axis, we're going to call Y1, right? And these areas here, the areas that these stresses are acting on, we're going to call A1. Right? So once I've taken that horizontal cut, right, now I am defining an area, which is the area above that horizontal cut, right? And that's still our neutral axis. Okay, so this is all we need now to be able to actually do some calculations. So the one thing you will notice here is that if the moment at C and the moment at D are not the same, right, then this cube right here, where I made the cut, is not in equilibrium, right? So what I need actually is I need a horizontal shear force there. I'm going to call it DH, H for horizontal. Right? And so this guy is a horizontal shear force. And it's needed when MC does not equal MD, right? And if that's the case, of course, that implies that sigma, the stress on face C, is not the same as the stress on face D, right? So hopefully you get this logic, right? We've taken this little, cross section out, this infinitesimal slice dx out. We've noticed that on the left-hand side I have MC, on the right-hand side I have MD. They're not necessarily the same because moments can have a gradient, right? And we've showed here that when those moments have a gradient, right? Well, when those moments have a gradient, all of a sudden I need a shear force, right? So if dm dx is not 0, then my shear force cannot be 0. Right? Then we zoomed in, and I replaced those moments with the shear, or with the normal force that they produce, right? The sigma equals my over I that we've been doing, right? And then I've taken a cut now, horizontal cut, and removed the bottom portion of this element, right? So this guy here, right, this, actually, you know what, let me do it this way. Let me highlight this guy in green, like that. And then let me highlight this guy in green. So you see, it's the same thing, right? I've just taken a cut. And now when I've taken that cut, as long as the MC and MD are not the same, which is in general the case, they're not always going to be the same, then I have to pick up this horizontal force there, right? It's the only way that I can maintain equilibrium in the x direction, right? So in fact, maybe what I can do here is put that this is sum of the forces in the x equals 0, right? So if the integral of mcy times I over a1 is not the same as mdy over I integrated over a1, then I have to get this shear force, right? Okay, so let me move forward here, and we can start to actually, solve for something. So here I will do sum of the forces in the x equals 0. I'm going to take positive to the right, as we always do. And I'm going to get that the horizontal shear force, which is positive to the right, plus this sigma c dA1, right? So I'm integrating sigma c over that area A1, right? And since that's moving to the right, right, I didn't show the arrows here, but I can show them, right? So that's moving, pushing the cube to the right. And then I'm going to have a minus sigma d dA1, over A1, and that is moving to the left. So that comes in as a negative, right? Okay, so now I can plug in this becomes mcy over I dA minus integral over dA mdy over I dA, and that has to equal 0. Now, at the cross section, right, MC and MD are constant, right? They do vary along x, but at a particular x, it is a constant, right? And I is also a constant, right? So this reduces to the following. So I can pull out MC minus MD over I, right? And that minus comes from that minus there, right? So if I pull that out, what's inside, right, the integral is the same for both cases. It's just y times dA, and that has to equal 0. Right? Now, if you look at the integral over a1 y times dA, that probably looks somewhat similar to you as the moment of inertia. Moment of inertia, remember, was the integral of y squared dA, and we referred to that as the second moment of the area. So here you might not be surprised to know that we are going to call this a letter. We're going to call it Q. And this is referred to as the first moment of the area. So Y is sort of your moment diagram, or moment arm. And so moment arm times area, that's where you get moment of the area. So this is the first moment of the area above y1, right? And again, y1, if you go back to the diagram here, right, y1 is just where we've taken that cut. So if y1 is 0, it's at the neutral axis, right? If y1 is negative, it's below the neutral axis. If y1 is positive, it's above the neutral axis, right? So that's the first moment of the area. We will talk about how to calculate that in a second, right? But now we can continue on. So dH now is going to be equal to md minus mc divided by I times Q, right? Now I did two things here, so please don't get confused. What I did was I pulled, so the y times dA, that just became Q, right? And then I moved that term, mc minus md over I times Q, I moved it to the other side. And when I did that, you can see the md became positive and the mc became negative. So I flipped them. So it's now md minus mc. That is just because I moved it to the right-hand side. Right, so I had to multiply by -1. Instead of keeping it minus MC plus MD, I just reorganized that a bit. And so then I can get this DH, right, is now V dx over I times Q. Right? And if you recall, so I'm going to do this over here. Right, so what I did there is I said, well, md minus mc divided by dx, that was, we just called that dm dx, and we said that that was equal to the shear force. Right? So I can simplify this or reorganize this, and I could say that this dm, which is md minus mc, actually equals v dx. Right? So this guy here is what I plugged in right there, okay? So md minus mc just became v dx, right? Okay, now I'm going to divide that dx through to both sides, and I get this vq over I, right? So that is really important. We're going to call this guy shear flow. So dH dx, so that is the rate of change of the horizontal shear force, right, per length. Right? We're going to refer to that as Q. We're going to refer to that as Q, and that is called shear flow. And it has units of force per length. So it is not a stress, right? It is a shear flow. All right. And so let me just rewrite this. And this will be the end of this particular lecture, right? But this is what we were trying to get to the whole time. So I'll box it twice because it's so important. And I'll make sure I star it, right? So this guy Q, this is shear flow, right? This guy V here is vertical shear force. So that comes from your moment or your shear diagram. Right? Q is the first moment of the area. That's fairly simple to calculate, similar to moment of inertia. And I is moment of inertia. All right, so that's where we are. Next time what I'm going to do is we're going to start an example, so you'll see how we're going to apply this to calculate shear flow. And then from shear flow, it's actually pretty straightforward. If you just divide shear flow by the width of the beam at any location, that will give you shear stress. So it goes from force per length to force per area, which is a